Okay, so the first thing that we would like to do is we would like to check that the Hamiltonian formulation of mechanics agrees with what we had from the Lagrangian. So remember, we were studying a particle moving in a potential, and we said for that problem, the Lagrangian is just given by 1/2 mx dot squared minus v of x. So that was the Lagrangian. Well, if I use this in equation 1, so I learn that P, which is the L dx dot, so what do I do here? Well, look at the first term. If I differentiate that with respect to x dot, I will just get mx dot. And the second term from the potential, that doesn't contribute at all. So now I know what P is. So let me use that inside equation 2. So from equation 2, H should be Px dot. So this is going to be m times by x dot squared minus the Lagrangian, which is 1/2 mx dot squared minus v of x. Now, whenever we move from the Lagrangian to the Hamiltonian, we're moving from a description in terms of x and x dot to a description in terms of p and x. So everywhere where we see x dots, we should rather write them in terms of p. And which equation do we use? Well, we use this equation that tells us p is equal to mx dot. This will change, of course, for the different problems that you study. But this equation tells us that x dot is equal to p over m. So then what is my Hamiltonian? Well, it will be m times by p squared over m squared. So after eliminating x dot, the first term is p squared over m. So now I've got minus 1/2. Oh, sorry, I dropped a square there. And the first term here, mx dot squared, will also be p squared over m. And then the minus times the minus makes it plus v of x. Okay, p squared over m minus 1/2 p squared over m is just p squared over 2m plus v of x. Now notice, the Lagrangian, which we had sitting over here, the Lagrangian was the kinetic minus the potential energy. The Hamiltonian, on the other hand, is the kinetic plus the potential energy. So this is just the total energy. And that's the interpretation of the Hamiltonian. It gives you the energy of the system. Good. Okay, so now let's work out our Hamilton equations of motion and see what they're telling us. So from equation 3, so x dot should be equal to dh dp. Well, here's our Hamiltonian sitting over here. Actually, let me box it. This is, I guess, an important equation. There's our Hamiltonian sitting over there. And what we should now do is we should calculate dh dp. So only the first term in the Hamiltonian will contribute. And after calculating that derivative, I just get p over m. Okay. From the second of Hamilton's equations, I learned that p dot is equal to minus dh dx. So now I don't bother to hit the first term in the Hamiltonian. I'll just hit the second term, and it becomes a normal derivative because v is only a function of x. It doesn't depend on p. Okay, so let's try to massage this a little bit and make sure it's equivalent to Newton's laws. Well, from this first equation over here, I've got p is equal to mx dot, and I can now plug it into the second equation. So p dot, well, I need to differentiate this again. This will tell me that mx dot dot is equal to minus dv dx, and this is nothing but Newton 2. So we have explicitly demonstrated that the Hamiltonian approach to mechanics gives us the same equation of motion as Newton 2. So we specified the Lagrangian, then we used the equations 1, 2, 3, and 4, and we reproduced Newton's second law. Now, the first, or one thing that we'd like to ask at this point, we've reproduced Newton 2. This was just a hard way of reproducing Newton 2. So you might ask, what is the Hamiltonian formulation good for? So one thing it's going to be good for is to make the transition to quantum mechanics. And I'm going to describe that later. But of course, the Hamiltonian formulation was written down well before we had quantum mechanics. So it must have some classical use. So what is the Hamiltonian formulation classically good for? And I just want to give you the rough idea. I'm not going to talk much about this at all. But the one-line answer is, well, it brings out, or it makes manifest, it exhibits, it brings out some geometry. It exhibits some geometry. It makes it clear that there's a nice geometrical picture. So let me just try to motivate that so that you understand what I'm saying. So let's again draw a space-time diagram. This is what we've been drawing the whole time. So here is t, here is x. Let's say I study a free particle, okay? If I study a free particle, then what you know is solutions just correspond to straight lines. So this is a perfectly good free particle solution. That one is moving in the positive x direction. Now let's draw a solution for a particle starting from here that's moving in the negative x direction. And what you notice is the two solutions cross at this dot that I've colored blue. So why can solutions cross? Okay, let's talk about that. So remember, to get a trajectory, to get a unique trajectory, so for a unique solution, you're solving the equation, you need both x and x dot, okay? There's two initial conditions because our equation of motion is second order at time. At that blue dot, these two particles have the same x, but they've got different values for x dot. And that's why they move away from this blue dot on different trajectories. So it's perfectly allowed in this description that trajectories cross. So trajectories can cross, okay? Now, I want to consider a different representation, and the one that's suggested by the Hamiltonian. And that's a description inside a space, not a space-time diagram, so not xt, but we now work inside phase space. And inside phase space, we have p on one axis and x on the other axis. Now, let's take a look. If you were solving these two first-order equations from Hamiltonian mechanics, okay, let me try to do something. Very good. So what is the initial condition? So to specify your initial condition, well, you have to tell me what is x of naught. That's from this first differential equation, from this one over here. And from the second differential equation, the one involving p dot, that you're also going to integrate. And to fix the constant integration, you need to tell me what is p of naught. So still two pieces of data, still two initial conditions, but the one is the initial x and the other is the initial p. So if I tell you on this plot that this is the initial x and the initial p, where that dot is, then there is a unique trajectory through this point. Let's call this point Q. And I can now draw a unique trajectory. So there's a unique trajectory through Q. You are not allowed, or there is no other trajectory that passes through Q. And what that means is, if you look for other solutions, they might hug the solution that you've got, so they might come very close to it. But inside phase space, trajectories never cross. So in phase space, trajectories never cross. Okay? And that's extremely non-trivial, that constraint. It gives us a beautiful constraint on the geometry of solutions in phase space. And this geometry is what is used to prove some of these beautiful theorems in classical mechanics, the CAM theorem, theorems about chaos, things like that. And it's really coming from this fact that trajectories never cross, and this is a property of phase space. So from a purely classical point of view, that was why people were interested in exploring the Hamiltonian formulation, because it comes with phase space and a beautiful symplectic geometry of phase space. We're not going to go into that in any more detail. We're now going to start discussing how do we make the transition to the quantum theory. And that's what we'll discuss next.